So this last part of the unit, okay, is not going to be involved really any curve sketching. So it's in the curve sketching unit, but it's not really involving you having to draw any graphs. You might have to draw something else though, but not graphs. So we're going to be looking at optimization problems. So optimization problems, you've actually been studying since grade 9, if not even potentially before in elementary in some cases. But in grade 9, the first optimization question showed up. I'm gonna pose to you an optimization question from grade 9 and see if you remember. Okay. A farmer wants to make a rectangular field and he wants to surround it with 20 meters of fencing. How should he set up his fencing to have a maximum area? You guys remember how that worked? Make it a square. Do you guys remember squares were the best rectangles? Like the optimal rectangle is a square. Okay. I don't know if you remember back in grade 9, we made you draw like all the combos, and it's like, okay, so 20 meters. So I could do 1 by 9, right? 1 by 9 would be 20 meters, 20 meters total. Okay. 2 by 8, right? 3 by 7. 4 by 6, and then 5 by 5, right? And my picture's not to scale because my 5 looks like less than 4, okay, so bad drawing on my part. But the idea is, if I calculated the area, 9 times 1, 9, let's just say meters squared, 8 times 2, 16 meters squared, 21 meters squared, 24 meters squared, 5 times 5, 25 meters squared, so I can fit still using the same amount of fencing, the biggest area occurred when I picked a square, okay? So the idea there is that I've optimized the situation because I've used, I have like some condition, some fixed amount, but I've maximized it so that I have a maximum area, or optimized so I have a maximum area, okay? Then you moved into grade 10, and the questions were a little more obvious, because what function, at that point we didn't call it a function, but what was the big theme of grade 10 math? You had to sum up grade 10 math with maybe one word. What would be the type of graph that you did a lot of in grade 10? Quadratic, right? What's the thing about the graph of a quadratic? There's a highest or a lowest place on a quadratic, i.e., and didn't we call it the maximum or the minimum, right, of the graph? Okay, and we use that to solve problems like even in grade 10 you were solving problems involving max area, area or the projectile, when's the max height of your ball, right, that got kicked, or this models your revenue, what's the maximum revenue. Those questions were grade 10 questions. The strategy used in grade 10 involved completing the square, if you remember, or getting into vertex form, that kind of stuff. We didn't know calculus then. And then in grade 11 and 12, we were introduced to a bunch of different other functions. And the focus on finding min and maxes weren't as important because they were harder to find. Quadratic's nice. It's an easy to pinpoint the location of a max or min because it corresponds to a vertex. As soon as you go into cubic or sinusoidal, right, now it's going to be more challenging. So the idea is now we want to be able to take any problem, whether or not it's quadratic or not, okay, and be able to find the absolute max or minimum value in the context of solving a problem. So it's not just, here's a graph, find the max. Now it's, here's a mathematical model, represents a real-life situation. What conditions cause a maximum or minimum to occur? Okay? And so we call this solving an optimization problem.
Excuse this interruption. Ms. Johnson, please, page 6033. Thank you.
So here are the steps we're going to follow. So it looks like it's a very daunting 12-step process, but I've just tried to break it down into each step should be pretty straightforward. So I'm going to read through them. So the first thing we're going to do is read the question carefully, identifying what the question's asking. Define variables. Sometimes they're nice and they'll define the variables for you, but if they don't, then you have to define your variables. Sometimes a diagram will be useful. identify the quantity to be optimized. So what are you maximizing, minimizing? Area, perimeter, volume, surface area, cost, revenue. Okay. Write a word equation or formula in terms of one or more variables for the quantity to be optimized. Okay. So that part is maybe not as, if you don't do that, it's not going to be the end of the world, but understanding in words what the relationship is an important thing, or at least represent it algebraically. Okay. Figure out what the independent variable is going to be. Sometimes you're going to see situations where there might be two variables involved, and we have to only have one. And again, you'll see that come up as we go through this. So then once you choose what the independent variable is, make sure all other variables are written in terms of that variable. Define the function, and then state any restrictions on the independent variable. That's another way of saying state the domain on which this problem exists. Okay? Then the last 4 steps is where calculus comes in. You guys get everything up to there is just building the model. But if you build the wrong model, you're going to have problems doing the rest, right? So you have to take the time to make sure your model is correct. Then once you have the correct model, differentiate, take derivative of the function. Solve for f prime at x equals 0 to identify critical numbers, because those will be your locations wherever f prime at x is 0, where you potentially have your min or maxes, right? And then confirm that the location of the critical point is the location of the min-max of the problem. So what I mean by that is, if I just figure out where the derivative 0, I'm not sure if it's a max or a min. So I have to do some other test, i.e. check to see that a sign change occurs. Or I could do the second derivative test, right? Find the second derivative, figure out the sign at that location to figure out if it's concave up or down, and then be able to classify as min or max. So we'll see that process as we go through the examples. Once you have the confirmation, now answer the question. It might be, what are the dimensions of the field? What are the dimensions of the box? How many items should you sell to maximize the revenue? Like, make sure you answer the question. So let's start looking at the different questions. So here's question 1 we're going to go for. So a lifeguard has 200 meters of rope and some buoys with which she intends to enclose a rectangular area at a lake for swimming. The beach will form one side of the rectangle, with the rope forming the other 3 sides. Find the dimensions that will produce the maximum enclosed area if there are no restrictions on the dimensions. Okay. So let's start. Do we agree that this is a very visual scenario, so a picture will help? So what would the picture look like here to represent this? We're roping off an area, a rectangular area for swimming. So we should draw maybe a rectangle. Now the one thing when you draw this rectangle that you might want to do is, how many sides of the rectangle are there going to be rope? 3 of the 4. So when you do the rectangle, you might want to just kind of do it like this, and then maybe just close it off with like a dotted line, or indicate with a different color that this is like the beach, okay? So the beach is here, so you don't have to put a rope along the beach, okay? But you need to put the rope in the water to cordon off, this is the swimming area versus this is not the swimming area, okay? So the other 3 parts here, so there's rope that starts on the beach, and the rope is pinned onto the beach there, but then it's going off into the water in a rectangular fashion. Does this make sense? And then this word buoy, this is like, just for those of us that may not know that word, it just means, it's like a kind of like a, in the water, it's just something that kind of, it's anchored down so that you can like post, like you can have like an anchor of a point in the water. So it's like, does everyone know what a buoy is? Yeah, you've seen them before in the water. Okay, it's like just one of those things that's kind of bouncing up and down with the tide, but it's anchored to the ground so that it doesn't move. Okay. So there are no restrictions to the dimensions, so there it is. So if I want to maximize the area, I want to find the maximum area of this. Right now I have nothing to maximize. I know area is going to be maximized, but I need some variables to represent. If I'm maximizing area, how is area relate? Like what's the relation between area? What piece of information do you need to calculate an area? Let's go with that. Length times width. Good old from like grade 6, right? How do you find the area of a rectangle? Length times width. So in this picture, I can put an L and a W, and maybe I'll start by defining, let L and W represent the length and width of the swimming area. Okay. Again, if you wanted to, you could do the let statements as separate let statements. Let L be the length, let W be the width. I just kind of tried to do a 2-for-1 special there. Okay. And so we've defined some variables. I put them on my diagram as well. Okay. And I put a W here and an L here. And technically, just to finish it off, what could I put over in here? I could put another W just to kind of have the full picture. And the goal is to have a maximum area. So I want the model that's going to model this is area equals length times width, right? So that's our good old formula for area. But I want you to understand that right now I look at this equation. I can't perform any calculus to this because do you see that I have two variables on the right side? I can only take the derivative if I only have one of those variables. I can't have two. Just think, if I was going to say, okay, I want you to graph this. You can't graph L and W and A. How's that work? Right? You can't. Okay. So this is where, in a question like this, if they didn't give us any specific info, we'd be done. We're like, I don't know. It's too vague, right? Too open-ended. But we were given one piece of specific information we haven't used yet. And that is that the lifeguard has a number of 200 meters of rope. So that's the condition on this problem. That's fixed. You have 200 meters of rope to create this 3/4 of a rectangle, or 3 sides of a rectangle. Okay, so how could I use the 200 with the picture that's there? Like, how does the 200 fit into the mix? It's the length of rope.
200 equals 2 plus
So do you agree that the 3 sides here have to add up to that 200? You only have that much rope. So you have to decide, you have this giant piece of rope and you have to turn it into a rectangle, right? There's lots of options of how you can turn it. You can go 1 meter, 1 meter, 198. You could do that. Is that going to be useful for swimming? Doubtful, but it is legal, right? So the goal is to come up with that relationship that no matter what, the sum of those 3 sides has to be 200. So can I write that? This is now a little bit of an aside, okay? So I usually do my asides for this with my picture. So I know that L plus 2W, or L plus W plus W, has to be 200 meters. What makes that useful is that if I have that relationship that has L's, W, only L's and W's, could I use this to replace either L or W here? So now the question is, what would you like to isolate over here? It really doesn't matter what the variable is here. Okay? What's easier to isolate here, L or W? L is a bit easier, it doesn't require any dividing, right? But you could, if you really like, I want to isolate W, you could. But it's just going to be not as clean. But L's easy. If I isolate L, what's just going to become 200 minus 2W. Don't make a silly mistake and divide by 2W. That would be bad. Okay, so 200 minus 2W. So what I've just done is I have written the length in terms of the width. Is everyone okay with me at my statement there? I have now an expression for length in terms of width. So if that's true in this scenario, then can I replace the L over here with 200 minus 2W? And do you see that by doing so, you now have turned your equation that's like a formula, you turned your formula into a function. Does everyone see what I'm talking about? So your formula, A equals L times W, if I replace L with 200 minus 2W, I now have only W's here, so now I can legally write it as a function because there's only one variable. W. If I put W in here, I just put the W's in here, like it's only one variable. Okay? Great. Okay. So now I have a function that represents the area. Okay? I think everyone's okay that we could distribute that W just to make this a bit easier to work with. So what if I distributed the W, it would be, I'm going to distribute it, and I'm going to do the W parts first. So negative 2W times W will be negative 2W squared, and then positive 200 times W is plus 200W. Okay. I want you to understand right now that apart from the function notation here, this could totally have been, this question could have been given to you in grade 10. Okay? In grade 10, we wouldn't have a calculus strategy right now. We have the strategy of saying, could you figure out where the vertex is? Yep, you could either complete the square with this, or you could have looked here and found the zeros and the midpoint max, okay, and found the dimensions that would cause this to be true using non-calculus strategies. But we're in grade 12 calculus, so we're going to use a calculus strategy instead. Before I do so, can you tell me what is the interval on which this function exists legally? Because now it's real life. It's not just random function graphed on the Cartesian plane. In real life, what is a W allowed to be numerically? What numbers are allowed for W? Well, W stands for the width. The width of something has to be. But what are legal widths of things? When I measure. Okay, positive. Technically, you're going to argue with me, but I'm going to hopefully convince you. Could you legally have a width of 0? Is having an area of 0 numerically okay?
Yes.
Okay, what you can't have is a negative area. That's illegal. But areas of 0 are legal. So what would cause the area to be 0 here if W was 0? Agreed? So the interval, or I'm just going to call it the domain on which W exists, the lowest W is allowed to be is 0. Based on this model, is there a maximum that W can be? So 200 would work. I think 100's better. Do you guys get, it's all about look at the second factor here. If you put in 200, you get a negative value. That's not good. But if I put 100 in, I would get 0, which I'm saying that's the limit of what's allowable, 0 for a length. So 100. So what I'm saying here is, not only is this the graph of this model only exists from 0 to 100. And if this was grade 10, at this point you might be going, okay, so 0 and 100 are my zeros. You guys know what you would do next? So if 0 and 100 are my zeros, where must my vertex be at? Good. Middle of 0 and 100 is 15. So, but you get that endpoint. There's nothing happening beyond. Even though the model technically is just, a normal quadratic that would keep going, all of this part of the graph is not possible because those would cause negative areas. Okay? 0 to 100 gives me these are all the possible areas that this roped off swimming area could be. They all exist. Every single area exists on this graph. This is like area and width. That's what you just created. The model you just created matches this picture. Okay? Well, now let's go calculus-wise. If I want to know what the maximum area is, what's the maximum area going to be on this graph? Where the 0 number areas go up, areas come back down. So there's a point where the area is the maximum, and it's at the vertex. What's the graphical feature that we've been focused on in this whole unit to tell if you have a max or min? Yep. Slope 0. So can I, everything I just did here, so everything I just did there, I don't need to actually do to answer this question, because if I have the model, can I figure out the location of that without needing a picture? I go to my model, that's a function, and what are the 3 things I'm going to do? Take instead of equal to? Then I'm going to solve for W, and that's going to, hopefully, fingers crossed, I get 50, right? So let's see. A prime at W is derivative of negative 2W squared is negative 4W. Derivative of 200W is 200. Gonna let A prime at W be 0. So I have negative 4W plus 200. So I have a linear equation here. The easiest way to solve linear is just isolate your variable. 4W is 200. Well, I'm getting a warm and fuzzy feeling. W is 200 divided by 4, 50. No, you could have, if you wanted to factor out negative 4W minus 50, totally fine. But linear you could do that. Okay, so W equals 50. Yay. Now, if it's quadratic, you know, we know it's the max based on our fact that we know it's a quadratic that opens down. But let's use a calculus strategy to justify. So how can I justify? Because right now all you justified is that the derivative is 0 here. But that could mean a min, potentially, right? This isn't enough. So how do I do that second step of confirming it's a max? Well, plug it in. That just gives me what the max area is. But if I want to like what the area at that location is, but I'm still not convinced it's 100% it's a max until I do one of two things. Yeah. Increase decrease chart, and then that will, since your sign changes from positive to negative, therefore the max occurs. Or you could do second derivative test. Take the derivative of A prime at W, plug in 50, see if you get a negative value. That would indicate concave down. So that's another way of doing it. So let's go with option 1. Let's go with the increasing decreasing chart. So the increasing decreasing chart. Okay, so here's one thing I am going to be picky about. What's the variable in this problem? W, so don't start throwing X at me. Right? Okay, so W. And again, we're so used to in these tables to always start like negative infinity, but is that, again, is that out the window? Can't pick negative infinity. What's the lowest W could be? Now, normally we're used to in charts like this that you're always round brackets. But you can actually legally include 0 as the lower bound here, because there's no horizontal tangent at 0. Does that make sense? So if you're like, no, I want to just keep everything open, that's fine. You guys want to keep everything open just to be like, let's be consistent. So let's keep it open. So 0 to 50, and then 50 to 100. And we have A prime at W and A at W. Okay, so, you guys hungry for burgers right now? No.
I was like, what?
I was like, what is going on?
So what happens if you do a test value into, here's your derivative. So if I put in a number that's between 0 and 50, guys, like 10, negative 4 times 10, negative 40 plus 200. Positive, so I know that my area function is increasing. Then I pick a number between 50 and 100, like 90. Okay. Negative 4 times 90 is negative 360. Negative 360 plus 200 is... Okay. Since A prime at W changes from positive to negative at W equals 50, therefore max area occurs at W equals 50. I'm not even going to worry about the word local or absolute here. I'm just going to go with just say max. Do you agree that if you have a sign chart that literally you have one key place and you only go up, down, then there's no other place that could ever be higher than that. So it's the max. It is. Okay? Okay. So conclusion, so make sure we answer the question. Find the dimensions that will produce the maximum area enclosed. So we want to find the dimensions. So We have the W. Man, I wish there was a way to find the corresponding L. You basically created the relation between L and W when you isolated. So I can find the matching L. L equals 200 minus 2 times 50. 200 minus 100 is 100. So conclusion, okay, so final conclusion. Okay, so the dimensions that produce max area are, now in this case, normally you would just, for rectangles we're used to just going big number times small number, but I think it's just better to go when L equals this meters and W equals this meters, so that if I'm ever confused of which side is which with the ropes, I can go back to the picture and go, oh, she means this is L and this is W. So L equals 100 meters and W equals 50 meters. And that was a lot of work to confirm something that, again, if you dust off the very, very far dusty corners of your brain, do you guys remember that you did look in grade 9 at the three-sided rectangle scenario? And the strategy was the optimal rectangle was when the length was double the width. You guys remember that? So like I'll just throw this at you. If optimal rectangle for all four sides is a square, right? So if a square is optimal, but then I say, but I only want you to put 3 sides, you have this whole extra bit that was normally here, right? What I can do is just say, hey, see that bit? I'm going to move it to there. And then I just take this piece, right, and move it over here. You see what I've just done? By not having to put the rope on that side, I doubled the other side, and that's the optimal rectangle when you only do 3 sides. The length is double the width, because you basically just took this side and just doubled one side. That's going to be your biggest area. Okay, again, what I'm just trying to remind you of, it's not a big deal if you don't remember this, because the focus for this course is to use the calculus strategy to find this out. But it's nice to have those kind of things just in the back of your mind to kind of confirm your answers. Okay? So everyone good with that question, how that works? Okay? So again, let's just go through what we did. We had a scenario where we created a model, we defined the variables, we came up with an equation, we set it equal to 0 and solved for, took the derivative of it, set it equal to 0, solved for your variable to figure out where the horizontal tangents are, confirmed that the location was the max, and then made our conclusion. So there is a part B to this, and the nice thing is you don't have to, a lot of what you need for part B you've already done, so you don't have to do a lot of extra stuff. But part B says, due to the depth of the water, the area cannot extend more than 40 meters into the lake. So what was we found that the optimal width for the biggest swimming area occurred when W was 50. What has essentially just happened if I say, to be safe, the maximum depth your rope can go is 40. What's just happened to the solution of 50? It's now, do you guys get it? Now 50 is extraneous. It's like if you look at this picture, essentially what I'm saying is, this is the picture if there's no restrictions. But now I've just restricted it that 40 is the max you can ever go. So now this purple graph is what you need to maximize. Purple graph. Well, do you get that the 50, since it's now, if now your domain is 0 to 40, 50 is now extraneous. Okay? So that's the idea. So the new domain based on this restriction is 0 less than equal to W less than equal to 40. So therefore W equals 50 is extraneous. Does that mean, okay, so there, I cannot put the rope out, I'm done, no swimming here? It doesn't mean that. It means that I just have a different max, like locate, the max is no longer going to be where a horizontal tangent is. Now I have to focus in on the endpoints. Okay, so determine, so it means determine the areas, determine area, A at W, at the endpoints. And I could argue to you that you could have done that in part 1, but do you get that both of your endpoints in part 1 would have been 0 meters squared, 0 meters squared? You kind of already knew based on the shape that the max is going to occur at the top. Here, if A at W occurs the endpoints, so the endpoints are 0 and 40, well, I just gave away what's happening at 0. If you put 0 in to, put 0 in to this model, what happens if you put 0 into negative 2 times 0 squared plus 200 times 0? The area you can, if you let the width be 0, the area you can swim in is 0 meters squared, right? But if I put 40 in, 40 isn't a it's not the bound, it's not another 0, it's now here. So I have to figure out this value, right? That value is going to be the max. So if I put 40 in here, negative 2 times 40 squared, or again, you put the 40 into the factored form or the expanded form. Negative 2 times 40 squared plus 200 times 40 gives me 4,800. Okay? So, of the two endpoints, obviously, that's bigger than 0. Okay? So the dimensions. So the max area will occur at W equals 40 meters. And again, just so that I finish this off, what would be the corresponding length? Again, it's the same formula to find L, right? L is 200 minus 2 times, in this case, 40. 200 minus 80 is 120. So again, you guys get the area 40 times 120, right? 40 times 120 is 4,800, whereas 50 times 100 was 5,000. So 4,800 versus 5,000. It's a lower area, but based on the restriction, this is the best it gets, right? I can never reach 5,000 because I can't go further than the 40. So the best I can do is to choose the 40 as the maximum. Just say the max I can go. I'm going to plot my boy there, and then create my rectangle. Does that make sense? So moral of story: you have to, if there's a restriction, you might have to adjust what solutions are allowed. And if none of the horizontal tangent solutions are allowed, then it's the endpoints that are going to be your options that you're going to look for. Okay? Okay. Let's do another example. Example 2. Okay. A cardboard box with a square base is to have a volume of 8 liters. Find the dimensions that will minimize the amount of cardboard to be used. So we're entering 3 dimensions now. Okay, 3 dimensions. So again, can we draw this cardboard box for ourselves? So it's a square base. So as soon as you see square base, because whenever you think box, most of us go default to LWH, right? Length times width times height. But if it's a square box, what's true about the bottom? We don't need 2 variables for the bottom. We can just pick 1. So typically what we end up doing is just to lessen confusion, we just go like x by x. Like x times x is the base with a h, height. So the volume of a square base box is going to look like that, x squared h. And here's my picture. Are you guys all good at your perspective 3D drawing? You draw a rectangle, you draw a parallelogram to kind of rhombus-y shape to represent your base, right? And then the goal is, once you have that, you draw like another rectangle kind of up here, and then you just kind of join it up. Yeah? Okay. We're gonna go x by h. So there's my picture. Okay. So I want to minimize the amount of cardboard. So I'm gonna, again, let's introduce some variables. I'm gonna let x represent the side length of the square base. And I'm going to let h represent the height. The goal is to minimize amount of cardboard. So amount of cardboard, what's that the equivalent for geometrically of this box? Like what if I want amount of cardboard corresponds to the what of this box? The surface area, right? The surface area is how much I use, right? How many like the actual pieces of the sides that go all together to create the box. So I need to so another way of saying this is minimize the surface area. Okay? Amount of cardboard is surface area. So I need an area formula. So I'm not going to use, I don't know if you guys remember, back in grade 9, we kind of let you use SA for surface area, SA to distinguish from area. You guys, we're just going to go with A because we don't want to think there's two variables about it. So we're just going to go area equals. So can we come up with a formula? Notice I'm not saying the word function yet, I'm just saying a formula that represents the area of all the sides of this box. So when you think of a box, how many faces, and I'll use that proper term, faces does a box have? 6, right? Top, bottom, front, back, side, left side, right side, okay? If you have a box in front of you, okay? So let's start with the top and the bottom are, in this case, specifically squares. So how many of those are there? 2 of them. So does everyone agree that 2x squared is the area of the top and the bottom? So now I need the areas of the front, back, and left and right sides. But again, because the base is a square, are all of the sides of this box the same? Like all the faces on the sides. Like if I want to find you guys get every side of this box is a rectangle with dimensions x by h, x by h, x by h, x by h. So how many x by h's or x times h's? 4. So everyone get that that's the area of a square base box. Right, there it is. Area of a square base box. Okay. So the goal is to make this a minimum. But can I take the derivative yet? Is there any red flag? Is there a red flag anywhere here? Red flag. Where's the red flag, guys? Let me plant the red flag. Where should I put it? Right? H, right? Problems, right? You can't be here, H. I can't take the derivative with you there, okay? Or, for that matter, X. I either need to get rid of X or H. Okay, probably H is the better candidate because I don't have to replace one H as opposed to 2 X's with a square. That means it seems like it might be tricky. So the idea is we need to somehow get rid of that H. So again, it's the same problem we came up with last time. I have a model, but I haven't used any specific info. But is there a specific restriction to this box that we're told numerically? The 8 liters. Okay? 8 liters. Liters is a unit of what, guys? Liters is a unit of volume, right? Liters, you buy pop or juice or milk, it's in liters. It's volume. Okay? Volume is liters. And the key here is we want to be able to relate dimensions of a box to a volume. Do you guys get that? Liters and milliliters are great for like measuring volumes of things like liquids and things. They're great. They're not as useful to get back into the units for measurement of dimensions. So there is a conversion factor from from liters to meters cubed, or milliliters to centimeters cubed is actually the easier one. Does anyone know the relationship between a milliliter and a centimeter cubed? Well, I want to rock your world, guys. If you never knew this, maybe you do know this, you just forgot. 1 milliliter is 1 centimeter cubed. So 1 milliliter is 1 centimeter cubed. So when you go buy your pop now, and you're drinking your can of Coke or whatever, right? And you think 1 centimeter by 1 centimeter by 1 centimeter, that's 1 milliliter. And so if you have a bottle of pop or your two liters of milk, there's 2,000 of these in your 2 liter of milk container, right? Make sense? Okay. So why is that helpful? Well, if 1 milliliter is 1 centimeter cubed, what would 1,000 milliliters be, guys? How many centimeters cubed? This isn't a trick question. If 1 milliliter is 1 centimeter cubed, 1,000 milliliters will be 1,000 centimeters cubed. Why did I pick 1,000? Because 1,000 milliliters is don't make me cry on the inside. 1,000 milliliters is in a liter. You guys not know your measurements? Milla, 1,000, right?
Got it.
Millimeter, meter, 1,000 millimeters in a meter, okay? Milligram, gram, 1,000 milligrams in a gram, right? I think I'm right. So 1 milliliter is 1 centimeter cubed, so 1,000 milliliters is 1,000 centimeters cubed. So what I'm trying to get at is 1 liter is 1,000 centimeters cubed. Yes? Are we okay? Okay. So that being said, if I go into the mode here, if it's an 8-liter container, okay, as I scribbled completely over it, okay, an 8-liter container is really how many centimeters cubed? 8,000. So 8 liters is 8,000 centimeters cubed. So that's going to be helpful based on that first thing I said, where the idea is I want to be able to replace H with something. I need to use a known relationship. Does everyone see that the known relationship is the volume to the dimension? So x squared H is equal to the volume. So x squared H equals 8,000 centimeters cubed. So what's H going to be, guys? To isolate H, what do you do with the x squared? True. So divide, and it would be 8,000 over x squared. Hello? Okay. There it is. That's the relationship between the height and the volume and x. So h is 8,000 over x squared. Again, you could isolate x there. There's nothing stopping us from isolating x there. But you get that if I isolate x there, what's showing up? Square root. That needs to then go into both of these you're going to have square roots of h's and stuff, right? It's going to be yicky. Whereas at least here, I don't have to worry about any square roots. So, you see that my area formula is now going to become an area function where a is going to be in terms of h's. No? Okay, like makes you happy? Okay. So 2x squared plus 4x open bracket 8,000 over x squared. Okay. So I don't want to take the derivative yet. Can I clean up the second part of this expression here? 2x squared, and then I have 4x times 8,000 over x squared. I can see two things you could do there. Numerically, what's like the one number you can write over here? 4 times 8,000. 4 times 8? 32, so 32,000. And then something kind of cool. One of the x's cancels, right? X squared. One of the x's cancels, so I have 3,200 over x. So this, over, what did I do? Oh, this is in terms of x's. I lied. It's not it's x. My bad. My apologies. Okay. Then I need the x there to match up with the variables on this side. If you decide to replace with h's, then you would have the h. My bad. Apologize. Okay. So there it is. You now have the model for the area of the box, all the sides of this box in terms of x, the base of the box, the base length of the box. So if I can take the derivative of this and set equals 0 and solve for x, then I'm going to get the location where there's potentially your minimum. Okay? Before I go further though, before I go into calculus mode, what values of x am I allowed to put in here? It's a little bit different than the last one. Okay? So if I said you have to tell me the domain of this model, what's the lowest number you could put in for x? Is 0 now, it's still the boundary, but can you include 0 this time? Because now 0 is showing up in the denominator. We can never have a denominator of 0. So 0 less than x, and then what's the upper bound? Is there any upper bound here? It's going to seem a bit strange, guys, but there's actually no upper bound. And I know it's going to seem silly, but mathematically speaking, if the bigger you make x, okay, there's still always a number you can pick that will be the matching height. Now that matching height might be like 1/billionth of a centimeter, but that's still technically a number. Okay, just think of it. I can keep picking bigger and bigger numbers for x. It just means I'm doing 8,000 divided by bigger and bigger numbers, but 8,000 divided by a number is never 0. It can get really super tiny, but never 0. So 0 less than x, or more appropriately, x greater than 0, that's really your domain. So this one's an easier domain. Just x has to be positive. That's your domain. No endpoints. X has to be positive. Okay. So now I'm going into calculus mode. So a at x equals 2x squared plus 32,000 all over x. Do you guys want to do a rewrite step first before we take the derivative? So a at x equals 2x squared. What's the rewrite? So if I'm about to take the derivative of 32,000 over x, it might be easier to just do 32,000 x to the -1. Beautiful. Okay. Derivative time. Here we go. So derivative of 2x squared. 4x. Derivative 32,000 x to the -1. Negative 32,000 x to the good. There it is. Derivative found. Okay. So we found the derivative. What's the next two steps in the process of finding where the optimal value of a at x? I have the derivative of a at x. This represents all slopes of the area function. Where do I want to figure out the slope? I want to figure out where the slope is, because those are your potential max and mins, right? So let a prime at x be 0. So I'm going to just copy this part. Now, don't make a silly mistake here. We'll want to rewrite this part with positive exponents. Is the 32,000 staying in the numerator, or is it going down to the denominator? It stays in the numerator, right? Because 32,000 is not raised to a negative exponent. Only the x is raised to the negative exponent. Okay, that's a common error people make. So minus the 32,000 is still up here, all over x squared. Okay. So now the goal is to solve for x. Now, an equation like this shouldn't be completely unfamiliar to you from advanced functions, solving rational equations. I'm hoping that what was stressed to you in the last course was when you see an equation like this that you have a rational part, a part that has x as a denominator, that your ultimate goal should be to get this to be a single expression. Because the nice thing about having a single expression equaling 0 is then you just have to worry about the numerator being 0. Does that make sense? Right now this 4x is just like hanging out. It's kind of confusing. How am I going to work with this 4x? But if I can make it part of the numerator of one big expression, and then I have fraction equals 0. Well, if I have a fraction equaling 0, the only time it's 0 is if the numerator is 0. So now I have an equation that's no longer a rational equation. Yeah? So, moral of story, you see something like this, what you do is you write it with a common denominator. So what's going to happen to 4x? If it now has a denominator of x squared, the 4x will need to become 4x cubed. X got to multiply it by x squared. The 32,000 isn't going to change at all. So there's my single expression equaling 0. Okay. You get, now you're going to zoom in on the numerator. So if this expression equals 0, then just the numerator really needs to be 0, right? First of all, the denominator can't be 0 because x isn't in the domain, like 0 is not even in the domain, so that part's irrelevant, okay? Doesn't matter, no matter what x that's going to work, it doesn't matter if you have a number in the denominator, because you're going to have 0 over number is 0, that's fine. Okay, so we don't have to worry about the denominator. So what I like to do is kind of say, therefore, I'm going to zoom in on the numerator and force the numerator to be 0. Again, whenever you have just single variable, a single variable here, the easy thing is just to isolate. So 4x cubed is 32,000. X cubed is 8,000. Okay. Are you getting warm and fuzzy, like fuzzy feeling like me inside here? You know, can you guys see what the cube root of 8,000 is going to be? Cube root. Cube root. So remember, number times number times number is 8,000. Doesn't always work like this, but we're gonna live in the world of beautiful numbers for today. Exactly 20. Okay. Okay. What have you just found? You have found that the slope is 0 there. You guys get that's not enough for you to confirm it's the min. I'm going to go with option 2 this time. Instead of going to increasing, decreasing chart, which you could totally do, I'm going to go to second derivative scenario. So second derivative test. So what that means is, go back to your a prime at x here. Can we find a double prime of x? What would a double prime of x be? Derivative of 4x. 4. Derivative of negative 32,000 x to the negative 2. Negative 32,000 times negative 2 will be positive 64,000 times x to the negative 3. So now, again, what have you just found? You found the second derivative. That's going to tell you concavity. If I plug in 20, the sign of this should tell me, is my graph opening up or down at that point? And based on that, I'll know if it's a min or max. Okay? I think you should already kind of know what's going to happen. Look at, you're going to do 4 plus 64,000 over positive number cubed. Are we all feeling it's going to open up? Concave up. So let's confirm it. So I'm putting 20 in. That's 4 plus 64,000 over 20 cubed. And just to confirm it, 64,000 divided by 20 cubed is 8. 8 plus 4 is 12. So we got a positive number. Okay? Since a prime at 20 equals 0, and a double prime of 20 is greater than 0, therefore, what is, again, concave up, again, what, do you guys get what these two pieces are telling you is horizontal tangent, concave up. Do you guys get those two pieces together tell you that what's happening? A minimum is happening. Yes? So the min area occurs at x equals 20 centimeters. And then usually that leads us to go right to directly to our final conclusion. We might have to calculate one little thing. Find the dimensions that will minimize the amount of cardboard used. Dimensions again. So you have the X. What's the piece you need to save the dimensions? H. Okay, I have a formula right here to find the height, right? Height equals 8,000 over 20 squared. 8,000 divided by 400 is 20. Okay, so therefore, this is my ultimate conclusion, the minimum area occurs when the dimensions are, this time I think we can get away with just saying them like we normally state dimensions. 20 centimeters by 20 centimeters by 20 centimeters. So again, what's shown up again, that the optimal 3D box is what shape? It's a 20 by 20 by 20 cube. Optimal 3D shape built with rectangles is a cube, because then each square will be minimized and therefore overall a minimum. Okay? This is the last time I think there's a part B, but again, I just want you to highlight why part B's might be important. So part B says, we're going to do this tomorrow. Okay. Well, we can maybe set this up. So the cardboard for the box costs 0.001 centimeters squared, but the cardboard for the bottom is thicker, so it costs 3 times as much. Find the dimensions that will minimize the cost of the cardboard. So if you get this, this is going to be a different model altogether. I've had students in the past answer this and then start throwing the money at the problem after they found this. You guys get that? If it's going to be more expensive to make the base, it's going to be, perhaps the minimum cost might not match up to minimum area, right? Because if you want to have the minimum cost, you'd like the base to be as small as you can make it, because it's going to be more expensive, right? So the idea here is, by adding that little complication in, a cube may no longer be your best bet. Okay? So the model here is going to change a bit. So first of all, notice that it doesn't say minimize the area or minimize the material. It says minimize the cost. So I would need a cost function instead, or a cost formula first. So my cost formula, okay, maybe I'll go. Cost formula is, so I'm going to go back to my area formula. Here was the area, guys. Remember, this is where we started. We built this by saying 2 squares for the top and bottom, 4 XHs for all the sides. What is it saying? It says that the bottom needs to be thicker. It costs 3 times as much. So if all the other sides are costing 0.001, what's 3 times as much? 0.003, right? 3 times 0.001 is 0.003. How much of the area is going to cost that much? Like what formula, what part of the box is going to cost that much per centimeter squared? 1 of the x squared. So 1 of the x squared. So 1 of them. Do you agree then the rest of the box costs 0.001? So it's your call of how you want to do this. You might want to go, so there's my other top, 0.001 of the top. That can be cheaper. And then 0.001 times the 4 sides. Everyone follow that? This might be one where you might want to write it in words, right? 0.003 times the bottom, plus 0.001 times the top, plus 0.001 times the side faces. So look at what we've got here. 0.003x squared plus 0.001x squared, 0.004x squared, like terms, right? 0.001 times 4, x 4xh is going to be 0.004xh. Can I now, if you guys get everything else from this point forward is identical to how we solved this, right? We're going to replace h with this thing. We're going to simplify. We're going to take the derivatives, take the zeros off it. But now it's not going to work out to the same number anymore. Okay? So since we didn't get close to finishing like our lesson today, guys, you guys want to give this a go and see if you can finish this? And it'll be the first thing we do tomorrow, but maybe can you try and see if you can finish this off? You have the model, follow the same steps we did in A, but do we recognize that everything's going to be a little bit different because now we have these coefficients that we didn't have before? Okay?
Just can you quickly go to the other slide? I'll take a picture of the goals.
This?
Don't worry.
Don't worry.
You missed.
There's this thing called a video that I record.
And those are gonna publish it so
Okay, so as you can kind of see, these questions are a little longer and like you have to kind of balance all this stuff, but we will get faster at them the more we do them. So, okay, enjoy a math evening. Make sure the assignment is in my hand by 2:40 today, please. Thank you. Okay. So just, I'll be here for a little bit, so just make sure before you give it to me. I'll either be here or in the office. Thank you.